The last episode, we created a Disney lighting effect with a DC voltage and an LED. This episode is to expand on that and use an AC power source and household lights. Working with electricity is dangerous and can cause serious injury or death if done improperly. Always use caution. The method to change the brightness of the lights will be done using the typical zero-crossing phase angle method with a Triac. A 10-volt AC power transformer will be used with a full-wave rectifier to power the Arduino, but the rectified waveform will also be used as part of the zero-crossing detection. I'll build a linear power supply to look after the Arduino with the rectifier and an LM317 adjustable voltage regulator and set the output to 12 volts DC. The zero cross signal is taken from the bridge rectifier positive terminal but before the filter capacitor. The bridge rectifier and filter cap are isolated by a steering diode. That signal is connected to the first Optoisolator's anode through a current limiting resistor, and the cathode is connected to the circuit ground. At this point, I'll continue to use the Arduino Uno and connect the Optoisolator's collector to the D2 interrupt 0 of the Arduino. The cathode of the Optoisolator is connected to ground through a current limiting resistor. The signal I get from the Optoisolator isn't as defined as I expected, but I am hoping that it will be suitable to trigger the Arduino input. Part of the Arduino interconnect remains the same, like the control potentiometers, but the output is taken from the D4 pin rather than the PWM of D3 in the previous episode. To isolate the Arduino output from the AC voltage, I'm using another Optoisolator, an MOC3020, whose anode is connected to D4 of the Arduino through a current limiting resistor, and the cathode to ground. Here's the part of the schematic that describes the interconnection between the second Optoisolator and the BT136 Triac. I separated the Triac to a breadboard where the AC and lamp load is physically isolated from the rest of the circuit. There are a few script iterations from the previous episode. The constants declaration are pretty much the same except for a few additions. I designated D2 as interrupt 0 and with the internal pull up to 5 volts. The interrupt calls a subroutine called zero cross on the falling edge of the pulse. I determined that I'd split each half cycle of the AC waveform into 123 steps, with each step being 8 milliseconds in length. The light intensity is determined by multiplying the length of each step with the number of steps determined by the control in the main code. This value represents the AC voltage phase position where the Triac turns on. The loops section of the script only happens when the counter in the zero cross trigger is 0. The surge section increases and decreases around the base light intensity and is based on the potentiometer setting. Determining if the flicker is to take place hasn't changed much, but the duration is now based on the number of 8 millisecond steps. Before adding power from the mains, I want to confirm and compare the input waveform of the first Optoisolator and D4 of the Arduino, and confirm the light level control range from off to full intensity. I'll also confirm the other 3 lighting effect controls. To avoid unexpected fireworks, I'm using this variable voltage regulator during testing, connected to the Triac input terminals. Just as a reminder, don't forget to subscribe. Click like if you do, and the notification bell for new videos. And if you have comments, please leave them below. I'll use a 100-watt incandescent bulb and connect it to the Triac output. I can use an LED style bulb, but not a fluorescent or CFL type. Turn on the power to the circuit, and then confirm that the variable voltage regulator is adjusted to 0 before turning it on. I'll set the light level to 50% and slowly turn up the AC voltage and confirm that there are no issues with the circuit. A quick check of the other effects controls. And I'm happy with the result. The effect is quite random and should add a plus to a haunted Halloween house display. The next step is to create a PCB and package the project into a chassis, but that's in the next episode.